we are dealing with today one of the important most chapters for JEE, that is current electricity. Most of you people might have seen the last year's paper, that of course is this year's only. I am talking of 2013 JEE paper. Most of the questions have appeared from electricity. That means his concentration totally or mainly is on electricity chapters. So one should have thorough knowledge about this particular chapter, and at the same time you people should have every concept related to this electricity topic. Not in fact one topic I am talking about: electrostatics, current electricity, electromagnetics, all the three put together. One should have complete idea and understanding about this particular topic. Then automatically you can score more in the final examination of JEE as such. So we are dealing with today some of the questions which have appeared in previous papers and which we people have felt them very important by model. Those concepts we people are dealing with today. I just start with the very first question, and remember all of you, as and when I read the question, while doing the question itself, while explaining the question itself, I'll deal with the entire theory, what is related to that particular concept as such, so that it will be useful to every student to understand the theory along with the solution of this particular question as such. That is the point. So let us start with the very first question as such. The VI graph for a conductor at temperatures T1 and T2 are shown in the figure. Then T1 minus T2 is proportional to, options are given this way. First option is given as cos 2 theta, second option is given as sin 2 theta, third option is given as cot 2 theta, and fourth option is given as tan 2 theta. In fact, this particular question, what we are taking up as the first one, is directly dealing with the relation between voltage and current. In fact, you know very well, the graph what has been provided to us, if you look at, current is given on x-axis, voltage is taken along y-axis. In addition to that, he has just given us two straight lines like this. This of course he has mentioned has been the graph when the temperature is taken as T1. This has been the graph when the temperature of the surroundings is taken as T2 respectively. And in addition to this graph, he has mentioned over here this angle as theta and this angle also as theta. This is the graph that has been provided to us. Now all of you should understand in this regard, when we deal with Ohm's law, then only we be able to understand the relationship between potential difference across a conductor and the current that is passing through the conductor. Just to recollect that aspect first of all of you know very well, at a constant temperature, when we people keep the temperature of the system constant, then the current across the conductor is directly proportional to the potential difference across the terminals of the conductor. In fact, all of you know Ohm's law, even though it may not be universal law, one can understand directly the exact relation between voltage and current whenever we consider a conductor as such. The more the potential difference across the conductor, the more is going to be the current that is passing through that. But one condition is to be mentioned carefully there, that is the temperature, which is supposed to be a constant. So exactly based on the same lines, he has made this particular graph. Look at carefully, all of you. This is the graph given at a constant temperature T1. The second line, whatever we have got here, the straight line, that is the voltage current relation when the temperature of the conductor is maintained at T2 degrees centigrade. That is T2 Kelvin maybe, because he is talking about both the temperatures given in capital letters as such. Capital letter of T, generally we refer to Kelvin temperature as such. We all know that one very well. So this is the concept. And this is the law by means of which this equation or this particular graph can be understood. If you take this way, you can understand that I is equal to V by R. In other words, V is equal to IR, we used to say. But all of you can understand from this, the slope of this particular graph. Slope is nothing other than tan theta, which of course gives you voltage by current, that is nothing other than resistance of the conductor. So I repeat once again here, the slope of VI graph that always provides us the concept of resistance of that conductor as such. What for means, mathematically speaking, slope when angle theta is taken with the x-axis, the slope is going to give us tan theta there. Tan theta over here is y by x, that is opposite by adjacent. Then automatically we can understand that is nothing other than the resistance part of it. So what you should understand from here, you look at first, I talk about the first straight line at the temperature T1. So what I can write here, the slope which is taken as tan theta. The slope here is nothing other than tan theta, is nothing other than resistance of this conductor. What for means, this tan theta is nothing other than R, V by I. So what is this tan theta here? It is no doubt V by I, which is resistance R. So what we should understand from this particular concept is, at this temperature T1, the resistance, if I take it as R1, automatically we can understand that R1 is nothing other than the slope which is equivalent to tan theta. But you can certainly understand R1 is directly proportional to absolute temperature there, because resistance is depending on temperature also. That concept also you people must have got in memory. In what way we people used to calculate the resistance at a particular temperature? Try to recollect that equation once again. I just remind you, R at a temperature T is equal to R0 into 1 plus alpha into T. This is the in fact relation between the resistances of a conductor at 0 degrees centigrade and at T degrees centigrade respectively. If I take R0, the resistance of the conductor at 0 degrees centigrade, and RT, that is the resistance of the same conductor at a temperature T degrees centigrade, then this in fact is the relation between the resistances at T degrees and at 0 degrees respectively. But you people all should understand one more point from this equation. What is it? Just look at this alpha carefully. That alpha, we generally call it as temperature coefficient of resistance. So what is that alpha called here? Temperature coefficient of resistance. So when we take temperature coefficient as alpha, remember carefully, alpha varies from material to material. That in the sense what? Copper, if I consider, its alpha value will be constant. Alpha value constant at that particular temperature, like we can think of, that is actually the concept. So if I take this slope is tan theta, which is proportional to R1 and which is proportional to T1. So what I can write directly from this point, please, T1 is proportional to tan theta. That is according to the first graph what we people are observing here at the temperature say T1 Kelvin. I hope you might have followed the first step here. Now check carefully the second straight line. This is also a straight line graph. That also is giving us the linear relation between V and I. That in the sense, when V increases, I also increases. And V by I remains constant at that particular temperature. So what we should understand now, this is angle theta. Look at carefully, I have made it very clear in the beginning. If angle is given with respect to horizontal, then tan theta becomes the slope. When theta is given with respect to the vertical, then slope becomes cot theta there. So what we should understand for the second one, please? Slope, which is cot theta this time, because this angle is given over here. That is proportional to R2. That is proportional to T2. So what we should understand from this one? T2 is proportional to cot theta. That is my second equation. So one should understand from this totally that at T1 Kelvin or degree centigrade, whatever you talk about, at T1 temperature, resistance is proportional to tan theta. At T2 temperature, resistance is proportional to cot theta. That is the concept. But what is it he is asking us to calculate? It is T1 minus T2 we just want. All of you understand carefully, one is tan theta and one is cot theta. Actually speaking, we just want the equation over here, that is T2 minus T1. What is this value of T2 minus T1? You just look at carefully. I can write this one cot theta minus tan theta. Observe this point carefully. Cot theta minus tan theta. What is a cot theta officially? Cos theta by sin theta minus sin theta by cos theta, which of course you can write cos square theta minus sin square theta by sin theta cos theta. See, simple mathematics. No physics is involved anywhere in this. The moment you have observed that T1 is proportional to tan theta and T2 is proportional to cot theta, the physics part of it is over. So you can say straight away understand cos square theta minus sin square theta, that is cos 2 theta as such. And all of you know well, sin theta cos theta we have. This sin theta cos theta, what do you find over here? This can be written as 2 sin theta cos theta divided by 2. That in the sense what? You can write sin of 2 theta divided by 2. This is the denominator. So what can we write now? This can be taken 2 cos 2 theta by sin 2 theta. You people all can understand cos by sin again is cot. So we directly can write 2 cot 2 theta. That is the value of T2 minus T1. But what is his question here? What is T2 minus T1 is proportional to what? That is the concept. So what can we write now? This implies T2 minus T1 is directly proportional to cot 2 theta. That is the equation. So what you people should understand from this? Whenever we consider Ohm's law, V and I graph for a conductor is a straight line passing through the origin. First point. Second thing, this particular straight line, whatever we are getting, depends on the temperature of the conductor. If temperature changes, automatically resistance also varies. When resistance changes, automatically the slope that is going to be changed, due to which we people are given here two different straight lines with two different slopes. Two different slopes means you should understand they individually are having two different values of resistances. That is the point what one has to understand. So if you just take up here, if angle theta is given with respect to the axis of current, remember this point carefully. If angle theta is given with respect to the axis of current, then slope becomes tan theta. If theta is given with respect to potential axis, then slope becomes cot theta. So in the case of T1, slope is proportional to tan theta, that is equal to tan theta. Here it is equivalent to cot theta. So automatically slope is proportional to resistance also. Therefore, we can now write resistance in turn is proportional to temperature. Therefore, T1 is proportional to tan theta and T2 is proportional to cot theta. Simple T2 minus T1. Come on, simplify that whole thing and you will be getting cot 2 theta. So, what is the correct option over here? You just look at first. He has given 4 options over there. Cos 2 theta, sin 2 theta, cot 2 theta and tan 2 theta. These are the 4 options. Out of them, which one we people have got now? Third option, which is C, that is given, is correct. So, cot 2 theta is the corresponding answer for this T2 minus T1 over there. This is the first question what we have, right? So, all of you, the moment this type of a graph that comes over here, you should identify the relation between V and I according to the concept of Ohm's law. That is the only statement which relates voltage with current across any particular conductor as such. But one thing more I just want to extend over here. This alpha value whatever I have given you as temperature coefficient of resistance, its value, in fact you must have read also, alpha if it is positive, then one should understand it is a conductor like. If alpha is negative, we should understand it is a semiconductor like. And of course, all the conductors, they come under ohmic category of resistances. And all semiconductors and semiconductor devices, they come under non-ohmic category. So when you talk of these resistances also, you can easily recollect the fact that if alpha is positive for any material, it should be ohmic conductor or ohmic material. Suppose if alpha you come across with a negative sign by any chance, then one should consider that one as a non-ohmic resistance as such. So that way, ohmic and non-ohmic category also, those categories also, you people can remember here itself from this equation. So this is the description and this one the solution for the very first question what we people have taken up here in this sequence. So the answer over here is, that is the point what we people have to remember for this first question as such. Let us check the next number here. The dimensions of metal block are given 100 centimeter by 2 centimeter by 2 centimeter as shown. The ratio of electric resistances between the square faces and rectangular faces is, recollect once again, square faces and rectangular faces, that ratio of resistances we just want. The options are given this way: 1:1, 25:1, 2500:1 and 50:1. There is a small figure given for that, I just draw that one. And what is the ratio he is asking between the resistances between square faces and rectangular faces? The correct option for this one is C. In fact, 2500:1 is the correct option which we people are going to get now. One thing you should understand, of course, the way they have given this problem, first of all, you see. You just can take up, there is a block like this. And what are the dimensions of this block? He has mentioned, you see there. This is 100 centimeter given. This is a 2 centimeter given. This is again 2 centimeter given. Suppose if I name them like this, A, B, C, D and E, F, G, H. If I just take like this, then all of you can understand by looking to this figure itself, square faces he is asking. A, B, C, D is one square face. E, F, G, H is the second square face. Two square faces we have. And what else he is asking? Rectangular faces. A, E, H, D is one rectangular face. B, F, G, C is the second rectangular face. So his question is, what would be the ratio of resistances between square faces and rectangular faces? That is what he is asked. Let me just remind you, first of all, resistance of any conductor, it other than temperature, it depends on two major factors, which in fact we call them as the dimensions of that particular material. For example, if you take resistance is proportional to length of the conductor and inversely proportional to area of cross section of the conductor. In fact, you know well, R can be written as rho L by A. This is the formula. And what is this rho over here called? It is specific resistance. Specific resistance of the material of the wire or of the conductor I just talk about. Conductor means what? It's material only. It is understood. The same has got another name also here, that is also called resistivity of the conductor. So either specific resistance you can call it or resistivity you can call it. In fact, every one of you know that one very well. Now based on this particular equation, this question has been framed. Look at first of all, these two are the square faces. I'm just representing with 1 and 1. Square faces are these two. Between these two, what is the resistance? Let us write a simple equation. I write R square faces. This is the formula, rho L by A. But understand carefully what this L represents. It is the length. What do you mean by length in such models? Length is nothing other than distance between those faces across which the resistance is to be calculated. I repeat once again, length is nothing other than distance between those two faces across which the resistance is to be calculated. So I can now understand it is rho into what is length now? Distance between these two faces is nothing other than 100 centimeter. So you can write the same thing this way, 100 into 10 power minus 2 meter. You can take that idea because 100 centimeter you can either write 0.1 meter or 100 into 10 power minus 2 meter. I am writing like that. What about the area part of it? Observe carefully. Area means simply the area of this face Here it is square face we are talking. So area of square face is what? L square. That side square we people used to take up. Therefore, 2 square, it becomes 4 into 10 power minus 4. Because 2 into 2, 4 square, that is 4 centimeter square we get. But all of us we know well, we have to convert that into SI units. So 4 into 10 power minus 4 meter square as such. This is my first equation. Don't simplify that one. While taking the ratio, automatically things get cancelled. What about the second one? What is resistance of the rectangular faces? Rectangular faces, that's what we talk about. Here square faces we people have considered, here rectangular faces we are considering. Now rectangular face means AEHD, that is the second one. The other face is the other one, that is BFGC, that's the one. Now rho will be same because the material is same. Rho stands for the value of resistivity of the material. Here material is same throughout, therefore rho will not vary. What next? It is length again. Just now I have told you, length is the distance between those two faces across which the resistance is to be calculated, I said. So between these two rectangular faces, what is the distance of separation? It is 2 into 10 power minus 2 meter. What about area of the rectangular face? Length into breadth. Length is 100, breadth is 2. So 200 centimeter square, I now can write 200 into 10 power minus 4 meter square. And his question is very clear now. R square faces by R rectangular faces. That by this. So you can certainly understand rho gets cancelled. 10 power minus 2 gets cancelled. 10 power minus 4 gets cancelled. What is now left over here? 100 by 4 into 200 by 2. This of course you can cancel 50 times. This you can cancel 50 times. So 2500 is to 1. That is the ratio. And what is the answer that is given corresponding to this? I have mentioned in the beginning itself. It is the C that is given the correct answer here. So once again I just mentioned the concept related to this. Resistance of any conductor that depends on length and area of cross section. How it will depends? Resistance is proportional to length, inversely proportional to area of cross section. So taking this equation, R is equal to specific resistance into L by A, this model question can be solved. Only thing you should understand is, or you should recollect is, L stands for distance between those two faces in across which the resistance is to be calculated. And A stands for area of that face what has been covered, followed, or what has been considered. So what is that face area? Either square area in the first case or rectangular area in the second. In fact, A is called area of cross section. That is the point you have to understand. So this is the correct answer for that. C is the correct option that is tallying with this answer as such. That is the second question for us. Let us switch over to the next question with a different model. One of the best models what we have of current electricity. This is one among them. I tell you, I just read out the question first. Two sources of equal EMF are connected to an external resistance capital R. The internal resistance of two sources are R1 and R2 respectively. But he has very clearly mentioned in the problem, R2 is greater than R1. If potential difference across the source having internal resistance R2 is 0, then He has given 4 options. You just have to pick up one out of the 4. First option is given capital R is equal to R1 R2 by R1 plus R2. Second option, capital R is equal to R1 R2 by R2 minus R1. Third option he gave, capital R is equal to R2 into R1 plus R2 by R2 minus R1. That is the third option. And fourth option he has given like this, capital R is equal to R2 minus R1. But truly speaking, most of you people must have got the idea by reading the question itself. The answer, correct answer for this one is the D. The fourth option, D, is correct for this. So option is known to us. Now let us check how to get and how to solve this particular model. He is talking about two sources of equal EMF are connected to an external resistance capital R. Let us draw a small circuit for that. There are two cells like this which now are connected across an external resistance capital R like this. What is the description of these two cells or the sources of EMF he has given? Try to once again look to the question. Two sources of equal EMF. So if I consider this EMF is E, automatically this EMF also will be E only. So that is the first condition what has been mentioned in the question as such regarding these two cells. And what next he said? Internal resistance of two cells are R1 and R2. That means they do have same EMF. Observe carefully. But they don't have same internal resistance. Internal resistances are differently given. So let us take this one is R1 and this one is R2. This is actually the description what has been given in that problem as such. And another thing what he has given, R2 is greater than R1. That is the relation what has been mentioned in the problem. Even this also we have to take it for granted while doing the problem. Now come to the next. Cell when is connected across a resistor, you need to recollect 2 points to mind. One, is the cell discharging in the system or charging in the system? There are two things we have to concentrate on. Whenever a cell is charging, underline the word charging there. Whenever a cell is charging, its terminal potential difference will be greater than its EMF. I repeat, whenever a cell is charging, its terminal potential difference will be greater than its EMF. Fine. If you take a cell is discharging by any chance, giving out its energy to the circuit, if it is discharging there, one should understand the terminal potential difference in such case will be less than its EMF. So one thing you should understand, while charging, that is one concept I just have given you. While charging, V is equal to E plus IR. And what is this IR called? This IR is called lost volts. Remember this wording, a wonderful concept. Lost volts. Whatever the voltage that has been lost due to the internal resistance of the cell, that is what is the meaning of that. If you take while discharging, while a cell is discharging, then V can be written as E minus IR. Even you can understand this IR again is lost volts only. Means what? V and E, the difference between these two in both the cases is equal to lost volts only. Either it is more by lost volts or it is less by lost volts. That is the concept. Now first and foremost, looking to this, you tell me first what would be the effective EMF of the system. For this, you need to recollect a basic equation. When cells are connected in series, EMF will be the sum of all their individual EMFs. So what we should write now in this case? E effective is E plus E. Because both are connected in series, EMFs are added up. So I can write this one as 2E. That's one. Secondly, what will now be the effective resistance in the system? There is one external resistance R and the internal resistance values 2 by number we have. One is R1 and one is R2. They are also to be added up to this, that in the sense R plus R1 plus R2, that now gives you the total resistance or effective resistance in the circuit. Then taking these two, what will be the current? All of you can understand current I is equal to E effective value by R effective value, E by R. So we can write 2E by R plus R1 plus R2. That is the total current that is passing through the entire system. That is the total current which is passing through the external resistance. So whichever thing you take about, it is the same. Current is same. Now the question is this cell discharging or charging? We have to understand that point. So if you look at these two are connected in series, and current of course will have a direction from positive side of the terminal cell to the negative terminal of the cell. That means this particularly either you take the first cell or second cell that is now discharging in this particular case. While discharging, what is the equation I have already written? So what we can write in this case, since the cell, second cell is discharging, what can we write? Its terminal potential difference is equal to E minus I into R2. Why am I writing R2? Second cell has an internal resistance R2. You can see directly there. So we can say this terminal potential difference is given 0 in the problem. I once again read that sentence from the problem. If potential difference across the source having internal resistance R2 is 0, which potential difference it is to be called, I said? It is to be called terminal potential difference. What is it by formula? E minus IR2. That value is given 0. So what I can write from this? E can be written as IR2. But already I have calculated the current passing through the system. So what is that value? It is 2E by R plus R1 plus R2 into R2. That is the concept. Now you can cut this E off. Cross multiplication gives you R plus R1 plus R2 is equal to 2R2. Then what can we write now? Capital R is equal to, bring these to that side. It is now R2 minus R1. Look at this particular option there. The fourth option that has been given as D over here, that is the correct option for this. If you look at R is equal to R2 minus R1. So such model questions, whenever you come across, two things mainly you should understand. What is the first one? When cells are connected in series, effective EMF of the system will be the sum of all their individual EMFs, 1. And effective internal resistance of the system is equal to the sum of all their individual internal resistances. So that is one area you have to concentrate on. And come to the second, while a cell is charging, the terminal potential difference V will be E plus IR. That means terminal potential difference will be greater than EMF. That is the point. When the cell is discharging by any chance, then terminal potential difference V is equal to E minus IR. There you can understand terminal potential difference will be less than the EMF of the cell. So these are the areas, if you are thorough with, certainly such model questions can be answered very, very easily. And one should understand this is one of the very, very important models of this particular chapter. Not necessarily with the same question may be given there, but similar model question may appear any time, any year in any paper like of JEE. Remember this concept carefully. Let us switch over to the next problem, problem 4. The resistance of the series combination of two resistances is S. When they are joined in parallel, the total resistance is P. If S is equal to N times P, then the minimum possible value of N is how much? Minimum possible value, remember that. Maximum value, no one will ask you. What for? Of course, the reason we will be knowing it now. So minimum possible value of N is how much? 4 options as usual. First option is given 4. Second option is given 3. Third option is given 2. And fourth option is given as 1. And all of you should understand the importance of this model. This question has appeared in 2004 IIT-JEE exam. Now of course there is no separate examination for IIT-JEE, but the point is this model is important here. That importance of the model we have to look into. So resistance of the series combination of two resistances is S. So what we can understand first of all, R series, when two resistances are connected in series, R1 plus R2 will now be their effective resistance. That value is given as S as the first equation I can take from the first sentence. What has been mentioned there, I am repeating once again. The resistance of the series combination of two resistances is S. So R1 plus R2 is equal to S. Fine. When they are joined in parallel, the total resistance is P, that's given. So you can understand R parallel, that is R1 R2 by R1 plus R2. That is given as, right, P. That is the second equation I can take. And what is given as the relation between these two in the problem? It is given that S is equal to N times P. This is given in the problem. The series resistance effective value is N times the effective value of resistance when they are connected in parallel. That is the concept. So what you should understand, S is equal to NP means R1 plus R2, that must be equal to N times R1 R2 by R1 plus R2. Now here you should consider the condition what has been mentioned in the question. What is he asking? You see the last sentence there. If S is equal to NP, then the minimum possible value of N is how much? Minimum possible value for N to be minimum. What is the condition? You people just have to understand. N will be minimum, right? For N to be minimum, R1 should be equal to R2. Mathematically also you can understand that one from this equation. Whenever R1 and R2 are equal, the value of this N can be minimum. So when R1 and R2 are equal, can't I write each one of them as R only? When R1 is different from R2, I can use 1 and 2 letter numbers over there. When R1 and R2 are equal, why to call R1 separate, R2 separate? I take them as R only. So R1 is equal to, R2 is equal to R. Just to substitute those values here. R1 plus R2, that now becomes 2R. That is equal to N times R into R, R square, by R1 plus R2, that is 2R again. So what happens here? You look at 1 R gets cancelled, 1 R gets cancelled. So N must be equal to how much? After cross multiplication, we get N must be 4. So what is this option? He has given you the very first option as 4, second option 3, third option 2, fourth option is 1. So what is the correct key for this one? The answer what we people can say is the very first one, that is A. But be careful first of all. Based on which concept he has framed this question. All of you know pretty well, resistances when are connected in series and when are connected in parallel, how to calculate the effective resistance we will be knowing. For example, if R1 and R2, say two resistances, when they are connected in series, for example, then what I can write? The resistance effective value when connected in series is the sum of their individual resistances. This equation is known to everyone. Exactly in the same manner, when these two resistances are connected in parallel this way, this I take it as R1, this I take it as R2, then 1 by R effective is equal to 1 by R1 plus 1 by R2. In other words, you can even write the same like this also. R effective is equal to R1 R2 by R1 plus R2. That is the equation. One more point I just want to mention here. Try to concentrate on that point carefully. When two or more number of resistances are connected in series, the effective resistance will be greater than the greatest resistances of the circuit. I repeat my statement. When two or more resistances are connected in series, the effective resistance will be greater than the greatest resistances of the circuit. For example, 1 ohm, 2 ohm, 3 ohm, 4 ohm, 4 resistances are connected in series. Which is the greatest resistance out of the 4? It is 4 ohm. The resultant will be more than 4. So it is in series circuit of resistances, effective resistance will be greater than the greatest. Exactly in the same manner, effective resistance in parallel combination will be smaller than the smallest. So these two areas you have to concentrate on. In series combination, effective resistance is greater than the greatest. In parallel combination, effective resistance is smaller than the smallest. Another thing is, when connected in series, it is the current that remains constant throughout the circuit. Remember that. When connected in parallel, it is the potential difference that remains constant. That is the second aspect of it you should remember. Exactly in the same manner, in series combination, potential difference across any resistance is directly proportional to the value of its resistance. So V is proportional to R, that is the concept. Whereas in parallel combination, current is inversely proportional to the value of resistance. So what is constant in series combination? It is current that remains constant. What is constant in parallel combination? It is the potential difference that remains constant. What are variables in series combination? Potential difference and resistance. How do they vary? They are directly proportional to each other. Exactly like that, what are the variables in parallel combination? Current and resistance. Now the question, how do they vary? They are varying inversely with one another. So these are the points, if you can remember directly or recollect them while doing this model problem, it's not a big task for you to solve such models. One of the good models what we have. So this is question number 4 for us in this sequence. Let us switch over to the problem number 5. I read out the problem first. A material B has twice the specific resistance of A. A circular cross-sectional wire made of B has twice the diameter of a wire made of A. Then for the two wires to have the same resistance, the ratio LB by LA of their respective lengths must be how much? Options are given as usual. The very first option is given as 1. That means LA and LB are equal. That is what he means. And second option is, that is 1 by 2. Third option is 1 by 4. And fourth option is 2. And the correct option for this one is the fourth option. In fact, that answer is going to be 2. In what way we get that? Firstly, understand the wording carefully. A bit of, rather what the way he has mentioned, you should not have any confusion in reading the question. Then only you will be in a position to understand which formula that can be taken up, in what manner we can change the values, and how to just finalize the result thereon. All the things, of course, one can understand easily. So let us read the wording once again and write the data provided. A material B has twice the specific resistance of A. You can definitely understand from this, material B, that means rho of B is equal to twice rho of A. That is what he means. Material B has twice the specific resistance of A. Fine. What next? A circular cross-sectional wire made of B has twice the diameter of a wire made of A. So, radius of cross-section of B is again twice the radius of cross-section of the wire made up of A. So, you people can understand the wire is going to have thickness like this. That thickness in the case of a cylindrical wire is called diameter. So, if diameter is twice, if he gives, it is as well understood its radius also is going to be twice. So, diameter 2 times or radius 2 times, that hardly matters for us. And what next he is talking? Then for the two wires to have the same resistance, that is the clue for us. In fact, you all know resistance directly is rho into L by A. We just have taken up the same formula in a different model question earlier. The formula is same, rho L by A. This can be written as rho times L by pi r square, because all of you can straight away understand it is pi r square is area of cross section of the conductor. Area, of course, whenever we deal with, we take surface area, area of cross section. Two different ways we used to consider area. But while calculating resistance, it is the radius of cross section, that's what we people have to consider. So area of cross section, when we consider that r corresponding to that formula gives you radius of cross section. So this is the formula for r. Now let us write first of all what is r of A, resistance of the first wire A. I now can write rho A into LA by pi RA square. Pi r square is the formula for cross sectional area. Look at the second. What about RB now? It is rho B into LB by pi RB square. But all of you know, according to the given values, rho B is twice rho A. That is the relation mentioned. RB is twice RA. That is the relation mentioned. So let us write those values. Rho B is twice rho A into LB divided by pi, you take as it is. RB is twice RA whole square. So how much it's now going to be? It is rho A LB by, this being 4, 2 gets cancelled twice, so pi into 2 RA square. That is the first equation, and this one is the second equation. But you can understand from the problem given, for the two wires to have the same resistance. So what is the meaning of it? RA must be equal to RB. The resistance of the first wire, resistance of the second are supposed to be equal. That is the point. When you equate them, what is it you are going to get? Rho A LA by pi RA square. That is the first one. What about the second one? Once again rho A, this time LB by pi into 2 RA square I can write. Now rho A gets cancelled here, pi gets cancelled here, RA square gets cancelled here. What is now left over? You check it. Here we have LA, length of the first wire. Here we have LB by 2. But in such cases, you should read the question thoroughly. Whether he is asking you LA by LB the ratio or LB by LA the ratio. In this particular problem, he is asking you to calculate LB by LA. So LB by LA is equal to simply 2. Suppose by mistake, if I write LA by LB, then I will be getting 1 by 2. That 1 by 2 option also is given in the problem. Third option is given, second option is given 1 by 2 only. And fourth option is given too. So what will be the correct answer for this particular question now? It is this D, whatever we people are having. The fourth option is the correct option for this question. I once again repeat, the value of resistance is nothing other than rho L by A. Rho is specific resistance or resistivity of the material of the conductor. L means the length of the conductor, A is area of cross section of the conductor. Another important point to be noted from this problem is whenever diameter is twice that of the other diameter, suppose if he gives, then it is understood radius also is equal to twice the radius. Diameter twice the diameter is as well equivalent to radius is twice the radius. So according to that concept, we people have obtained the fourth option correct for this question over here. So correct answer for this one is D, that is 2 will be the ratio LB by LA now is equal to 2. This is problem number 5. Let us check the next problem, problem number 6. The resistance of a bulb filament is 100 ohm at a temperature of 100 degrees centigrade. If its temperature coefficient of resistance is 5 into 10 power minus 3 per degree centigrade, its resistance becomes 200 ohm at a temperature of, that is the question. 4 options as usual have been mentioned. First option 300 degrees centigrade, second option 400 degrees centigrade, third option is 500 degrees centigrade, and fourth option is given 200 degrees centigrade. The correct answer for this one is B, that is 400 degrees centigrade. One thing you should understand, according to the problem given, what are the values he has mentioned? Let me just write down the data. After that we shall discuss what is the theory behind that. Resistance of a bulb filament is 100 ohm at a temperature of 100 degrees centigrade. So at 100 degrees centigrade, the resistance is 100 ohm. So you can take this one as T1 degree centigrade and this one as R1, the corresponding resistance. And what next he is talking? Alpha value is provided. Already we have discussed alpha in one of the problems earlier. It is the temperature coefficient of resistance. So alpha is given 5 into 10 to the power minus 3 per degree centigrade. That is the value of alpha that has been mentioned. Now what next he is asking? Its resistance becomes 200 ohm at a temperature of what? At what temperature the corresponding resistance becomes 200 ohm? This is the question what he is asking you. What is the temperature at which the resistance now becomes 200 ohm as such? That is the art. But look at carefully first of all. Resistance is directly proportional to temperature. In fact, that is the reason why while discussing Ohm's law, we keep the temperature constant and then we relate potential and current. Otherwise, if temperature varies, automatically the resistance may vary in that without a change in V and I respectively. Therefore, you should understand resistance in this case is directly proportional to temperature. Directly proportional to temperature when I write, you can remember one point. Look at, say, at 0 degree centigrade, the resistance of a conductor is R0. I have increased the temperature to T degree centigrade. Then let us take the resistance has become R1. Imagine I have increased the temperature to T2 degree centigrade. Then the resistance has become R2. So just observe this particular concept carefully. At 0 degree centigrade, resistance of a conductor is R0. At T1 degree centigrade, resistance is R1. At T2 degree centigrade, resistance is R2. Now, taking this pair, how to relate R1 and R0? You must have got that idea. R1 is equal to R0 into 1 plus alpha T1, where alpha is temperature coefficient of resistance of the material of the conductor. So, if you take R1 is equal to R0 into 1 plus alpha T1, similarly, relate the first one and third one, please. That is, relate R2 with R0. So, what do you get? R2 is equal to R0 into 1 plus alpha T2. Similarity you see carefully. Both the equations are similar. Only values are different. There the temperature is T1, here the temperature is T2, here the final resistance is R1, here the final resistance is R2. Suppose taking this as first equation and this as second equation, if I divide one by the other, R1 by R2, I will get it as 1 plus alpha T1 by 1 plus alpha T2. If you further simplify this one, you get the formula for alpha. I directly write that equation. What is that equation now? R2 minus R1 by R1 T2 minus R2 T1 per degree centigrade. I repeat, temperature coefficient of resistance alpha is equal to R2 minus R1 by R1 T2 minus R2 T1 per degree centigrade. So, already you might have got this description. R1 is the resistance at T1 degree centigrade. R2 is the resistance at T2 degree centigrade. Alpha is temperature coefficient of resistance of the material. Same formula we have to apply here. That is the equation actually what is to be remembered for such models. Now what is alpha here? R2 minus R1 by R1 T2 minus R2 T1 per degree centigrade. Now what is R2 you know? It's 200 minus 100. R2 minus R1. Then R1 is 100. What is T2 I don't know. In fact that is to be calculated. Minus R2 that is 200 into T1 that is given as 100. And you know pretty well what is the value of alpha given. It's 5 into 10 power minus 3. So what can we write now? 5 into 10 power minus 3 is equal to, difference is 100 by 100 T2 minus 2 into 10 to the power 4. You can all understand 200 into 100 can be written like this. Now bring this one this side and simplify this whole lot. 100 T2 minus 2 into 10 to the power 4 is equal to 100 by 5 into 10 power minus 3. That is 20 into 10 power minus 3. That is 2 into 10 to the power 20 into 10 power 3 or 2 into 10 power 4. Look at this conversion. 5 goes in 120 times into 10 cube. So 2 into 10 power 4. Bring this one that side. You be getting 100 T2 is equal to 4 into 10 to the power 4. So what next? Therefore, T2 is equal to 4 into 10 power 4 by 100, which now becomes 400 degrees centigrade. So out of all the 4 options, I have already mentioned in the beginning itself, second option is correct. which is 400 degrees centigrade. So you can say the correct answer, that is the second option B. You should understand it's 400 degrees centigrade. But doing the problem is not a difficult task, provided you can remember this formula. This formula is the base for working out such model questions. So R2 minus R1 by R1T2 minus R2T1, that is equal to temperature coefficient of resistance. That's units, of course, we know per degree centigrade is the unit of alpha. So this is the formula based on which we have just worked out this problem. So the correct answer for this one is 400 degree centigrade. This is question number 6. Let us switch over to problem number 7. Altogether a different model question. One of the best problems ever we find generally. 7th question, let me read out the problem first. The ratio of the concentration of electrons to that of holes in a semiconductor is 7/4. Then what will be the ratio of their drift velocities? So first and foremost, let us first of all discuss what is this concept of drift velocity. Whenever we pass current through a conductor, we all know by basics, current used to flow on the surface of the wire itself. Current will not enter inside. Along the surface of the conductor, current flows. Now in this particular case, with what velocity the electrons or holes are drifting from one end to the other end, are moving from one end to the other end, that velocity we call it as drift velocity. If I take drift velocity as Vd, its formula is I by NEA. First recollect this formula. I stands for the current that is passing through the conductor. N is electron density. You should understand this is N is electron density. What is this wording? Electron density is nothing other than number of electrons per unit volume of the conductor. Number of electrons per unit volume of the conductor. This itself we otherwise call it as concentration of electrons also. So electron density you can call it, or number of electrons per unit volume you can call it, or electron concentration you can call it. So if you look at this equation carefully, when current is constant, charge is same, area of cross section is same, then what can I write now? Terminal drift velocity is inversely proportional to electron density. When I take this one as electron density, I can write it as Ne. If it is due to hole motion, the movement of holes, in fact you all know well, even hole is nothing other than the deficiency of an electron. It is treated to have positive charge. The deficiency of electron is called hole. You find holes mainly in the case of semiconductors. So in semiconductor, electron current will be there, hole current also will be there. So if I just take for holes, drift velocity is proportional to hole concentration. So for electrons, drift velocity is proportional to electron concentration. And for holes, drift velocity is proportional to hole concentration. So this part you people should have in memory to work out this particular problem. I read out the question once again. The ratio of the concentration of electrons to that of holes in a semiconductor is 7/4. Concentration means, just now I have told you, Ne by NH, that is given 7/4. That is electron density by hole density. Number of electrons per unit volume by number of holes per unit volume. That ratio is given as 7/4. Then what will be the ratio of their drift velocities? That is the concept. See, 4 options are given: 5/8, 4/5, 5/4, 4/7. Correct option is the 4th one, that is D now. Reason for that one you can understand straight away. When we know Ne by NH is given as 7/4, Ne is proportional to 1/Vd. So what can we write now? But we know well, Ne is inversely proportional to drift velocity of electron, and NH is inversely proportional to drift velocity of holes. So what is the question he is asking you? Their drift velocities, we want a drift velocity of electron by drift velocity of hole. Come on, take these two equations. Ne by NH is equal to VH by VE. VH stands for drift velocity of holes. This is drift velocity of electrons. But his question is drift velocity of electron to hole ratio we want. So what we should write? Drift velocity of electron by drift velocity of holes is equal to NH by Ne. You know Ne by NH is 7/4. Come on, reciprocate that. Won't you be getting 4/7 now? So what is going to be the corresponding value he is asking? What is the ratio of drift velocity of electrons to that of drift velocity of holes? Drift velocity of electrons to hole ratio, that is equal to hole concentration divided by electron concentration. So which of course is given 7/4 is electron concentration by hole concentration in the problem. Now reciprocate that, you be getting 4/7. So what is the correct answer for this question? 4/7, which is given as D, that is the correct option for us. So in reality, problem is not a lengthy one, but one should understand how the hole concentration depends on the drift velocity of holes. Similarly, how the electron concentration depends on drift velocity of electrons. They are inversely proportional to each other. If you can understand that one, this problem is just like that. Not even 5 seconds it takes for you to answer this question. So that is the point. That's the question number 7 what we have in this order as such. Let us check question number 8. That is, say, 8th problem we are dealing with. Let me read out the problem first. If the value of each resistance connected in the network is 10 ohm, find the current in the arm AD. A small circuit has been given here. And let me draw the circuit first for you people, so that you can think of what is the corresponding answer for that. The circuit is given this way. One resistance here, one more resistance here. That is what has been mentioned. One more resistance is connected this way, one more like this, one more like this, and one more resistance is connected here. In addition to that, one more resistance is connected in between also. Here very clearly he is mentioning this is the input terminal, that is current is entering this way and current is leaving this way. That has been mentioned very clearly. Given that this is A, B, C, D, E and F. Each resistance is R like given. Every value is R only. And mentioned there in the problem, each resistance is equal to 10 ohm. So let me read the answers also. His question is what? What is the current in this branch? That is the question. Current in the arm AD. That is the question. And options are given this way. I by 5 is the first option. 2I by 5 the second option. 3I by 5 the third option. 4I by 5 the fourth option. Out of them, the second option is correct. 2I by 5 is the corresponding answer for this question. But how come? First of all, understand this is 10 ohm given. This is 10 ohm given. This is given as 10 ohm. Even this also is 10. Here 10. Here 10. Here also 10 ohm. What is the basic concept we need to know to solve such model questions? All of you are familiar with the concepts of Kirchhoff's laws. Any circuit, whenever you want to analyze that circuit, we prefer taking Kirchhoff's laws. In fact, every one of us we know, Kirchhoff has given two statements. The very first statement is called law of currents. You can even call this one as junction rule. What is this junction rule? I just will remind you. When you consider there is a junction here where several currents are leading to that point and several currents are leaving that point. I repeat my statement. Few currents are going towards the point, reaching the point, and few currents are leaving the point. If I consider I1 and I2 are reaching O, I3, I4 and I5 are leaving O, then according to Kirchhoff's first statement, that is junction rule, algebraic sum of currents across any junction in any circuit is equal to 0. Algebraic sum of currents across the junction in any circuit is 0. What do you mean by algebraic sum first of all? If I consider incoming current as positive, I should take outgoing current as negative. And you people should understand straight away, if incoming is taken negative, then outgoing can be taken positive. That means there is no such restriction. This only should be positive, this only should be negative like. If incoming becomes positive, outgoing automatically becomes negative. If outgoing becomes positive if I take, then incoming automatically becomes negative. That is the way we people have to add them. So according to this equation, incoming if I take them positive and outgoing negative, I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. This is called algebraic sum of currents. You can even repeat the same this way also. I1 plus I2 is equal to I3 plus I4 plus I5. Observe the wording carefully here. Sum of incoming currents is equal to sum of outgoing currents. This is the first statement given by Kirchhoff. So for analyzing any circuit, we need to remember this law. Second, what is the second one? That is called law of networks. You can even call it as law of EMFs also. While taking law of networks or law of EMFs, one should understand conventional signs carefully. Suppose if I take a small circuit like this, two resistances say are now connected across this one, a cell like this. This is the cell. This is negative, this is positive, EMF is E, R1 and R2 are the resistances. Observe with this particular case, how can I just write the second law? If I take the direction of conventional current, it is always from positive side to negative side of the cell. It's a fact, of course, every one of us we know. After reaching here, this current becomes I1. I1 travels all the way across R1. And this current becomes I2. I2 travels all the way across R2. They mix up here to give the total current as I. If I just name these points like A, B, C and D, what this law of networks or EMFs that states? Sigma V is equal to 0. Algebraic sum of EMFs across a closed electrical network will be 0. I repeat, algebraic sum of EMFs across a closed electrical network will be 0. If I write the same this way, sigma IR is equal to 0 also I can write. But while applying this law only, you should understand one convention. If I take this closed circuit A, B, C, D, A, it's a closed circuit, no doubt. While taking this closed circuit, what is the convention we follow? If you move across the circuit along the direction of current, I repeat, if we move across the circuit along the direction of the current, that current should be taken with a negative sign. If you move opposite to the direction of the current, take that current as positive. I hope you might have recollected back the condition. When we move along the direction of current in the circuit, I should be taken with negative sign. When we are moving opposite to the direction of electric current, then I should be considered as positive. Another thing, while moving across a cell, from negative terminal, if you are moving towards positive terminal, then that EMF should be taken positive. From positive terminal, if you are moving towards negative terminal, then that EMF should be taken negative. So if you can remember these areas thoroughly, doing such model questions will be very, very simple. So I am just dealing with the second law over here. Sigma IR is equal to 0. I consider that particular law to solve this problem. Let us first of all see A, B, C, D, A is a closed network. Let us consider current is entering as I. It is going across this one as I1. Then how much is the remaining current here? I minus I1 is remaining. That is entering into this. After reaching B, I2 current suppose is going across this. Then how much will be the current that is passing through this one now? I minus I1 minus I2. You will be getting the value over here, I minus I1 minus I2. So that is the current across this. Same current, I minus I1 minus I2 comes all the way like this. In the meantime, what is happening? This I1, it enters into this particular resistor. This I2, it just comes all the way across the second. Both the currents will merge here to give out the total current here as I1 plus I2. So I1 is coming and reaching this point C. I2 is coming from D to C. Both will merge here to enter into this resistance as I1 plus I2. Same current I1 plus I2 reaches this F. In the meantime, I minus I1 minus I2 also will reach there. If you add these two, I1 gets cancelled, I2 gets cancelled, I will come out. So what is actually happening here? Individual resistances may take different currents, but whatever is the incoming current, same will be the outgoing current also. What is the meaning of that? One should understand the charge, whatever we are finding of the system, is always conserved. There will not be any loss of charge anywhere. Then there will never be any loss of charge even when taking up the current part of it also. Now look at what is the application of second law of Kirchhoff over here. I take the first closed network A, B, C, D, A. Look at A, B, C, D, A. I take that first circuit. I am moving from A to B, going along the current direction. So that current should be taken with a negative sign, I have already reminded you. So how to write that? Minus I minus I1 into R. Right? Here. Again I am going along the direction of current. Minus I2 into 10. That is IR. I am coming from C to D, but current is coming against my direction. Then I should write plus I1 into 10. And when I reach from D to A, when I am going back, current again is opposite to my direction. So I should take plus I1 into 10 is equal to 0. Just observe this equation thoroughly. A to B, I am moving along the direction of current. So by convention, we take that current with a negative sign. So minus I minus I1 into R. R is 10. Minus I2 into R. That is again minus I2 into 10. CD if I take plus I1 into 10 and DE plus I1 into 10. Now simplify this equation. What do you get? This implies minus 10I plus 10I1 minus 10I2 minus, that is plus 20I1 is equal to 0. Now 20 plus 10, 30. So we can write 30I1 minus 10I2 is equal to 10I. This 10I, if I bring it this side, this simplifies to 3I1 minus I2 is equal to I. This is my first equation. So observe the way what I have done. I have taken first closed network and I have written the equation according to second law of Kirchhoff. Now you take the second circuit, please. B, E, F, C, B you take. I write the same. B, E, F, C, B. Same. Write down the equation. Minus I minus I1 minus I2 into 10. This value. Next. Minus I minus I1 minus I2 into 10. Again this value. This one plus I1 plus I2 into 10. This value. Now this one plus I2 into 10, that is equal to 0. Once again look at carefully. Minus this current into resistance, minus this current into resistance, plus this current into resistance, plus this current into resistance, that sigma IR is equal to 0. That is my second circuit and this is the result of that. Now simplify this. What will you get? Minus 10I, right, plus 10I1 plus 10I2 minus 10I plus 10I1 plus 10I2. This one plus 10I1 plus 10I2 plus 10I2 is equal to 0. Now how many I1s we have? You look at 10I1, 10I1 20I1, 10I1 30I1. So I should write 30I1. What next about I2 you see? 10I2 plus 10I2 20I2, 30I2, 40I2. So plus 40I2 is equal to, that is minus 10I minus 10I 20I, that coming that side it becomes simply 20I. So this is the equation which can be rewritten like this: 3I1 plus 4I2 is equal to 2I. This is my second equation. So 3I1 minus I2 is equal to I. 3I1 plus 4I2 is equal to 2I. Now simplify just by solving them. What is the current across AD is my question. So what should I write? I1 I should calculate. So what next I should do? Take the first equation. I1 I want. Therefore, you multiply this I2 by 4. So what will you get? 12I1 minus 4I2 is equal to 4I. I have multiplied the first equation by 4. And second one you see, direct you take this equation. 3I1 plus 4I2 is equal to 2I. Now adding, I2 gets cancelled. Then what is left over? 15I1 is equal to 6I. Then I1 is equal to 6I by 15, which is 2I by 5. If you just look at carefully, 2I by 5 is current across AD. That only is the question he is asking you. So what can we write? I1 is equal to 2I by 5. That itself is current across AD. So what is the corresponding answer for this one? It is B. That is the correct option for us. So one should understand from this type of a model, one should be thorough with both the laws of Kirchhoff. One is law of currents, that is junction rule we call it, and one is law of networks, or law of EMFs also we call it. So according to the second law, by applying that, I have got two equations. Solving them, I have got current. That current itself is the current passing through this particular resistance, that is AD. Is how much is the question. So 2I by 5, that is the corresponding answer for us. So correct option for this question is the second one, that is B, which is correct over here. This is question number 8. One of the best models we have, and one should be perfect and thorough with Kirchhoff's laws, particularly the second law of Kirchhoff is more useful in different circuit diagrams as such. That is the concept. Let us check the question number 9. In fact, ninth problem, he is just dealing with some ratios. Whenever ratio problem that comes, in a very easy manner, you all can directly do that. What is the methodology we have to adopt for that? I'll give you. Let me read the problem first. 3 wires of same material. In fact, while reading the question itself, every student can directly understand some hidden values there. Some values will not be exposed in the problem. You will be finding that problem's idea. The person whosoever is giving the question said 3 wires of same material. First and foremost, same material, the moment you find that wording, it is understood the material has got constant value of specific resistance. That means all the 3 wires have the same specific resistance. That is the meaning of that wording same material. Are connected in parallel to a source of EMF. The ratio of lengths of the wires is 1:2:3 and ratio of their areas of cross section is 2:4:1. Then match the following. For matching the concept, first you should understand the table 1. He gave ratio of their resistances. Second bit, ratio of electric currents. Third bit, ratio of powers. And you have been given in this table 2, 6:6:1, 1:6:1, 1:1:6. This is the table 2. Table 1 is to be matched with table 2 now. Okay, options if you look at, the correct option for that one is, for first bit, that is ratio of resistances, you will be getting 1:1:6. And for the other two, you will be getting 6:6:1. So correct answer for this one is the third option. For A it is R, for B it is P, and for C also it is P. So first thing, 3 wires of same material are connected in parallel to a source of EMF. Understand that wording first. If I consider 3 resistances like this are connected in parallel, that is actually the meaning of it. And you should understand it is now connected across a cell like this. This gives the required potential difference to the system. Let us take this one as R1, this one as R2, this one as R3. This is what has been described there. What he has mentioned, length ratio of all the 3 wires, L1:L2:L3, that is given 1:2:3. Likewise, ratio of areas of cross section, A1:A2:A3, it is given 2:4:1. That is the ratio. what has been mentioned there. Fine. But we are taking their resistances here. Resistance is equal to rho into L by A. That is the formula. Every one of you know already, I have discussed in the beginning of this problem. Same material means rho is going to be constant for all the three wires. Then what you can understand here, R is proportional to L by A. That is the formula. When R is proportional to L by A, can't you now write R1 is to R2 is to R3 is L1 by A1 is to L2 by A2 is to L3 by A3. This is the first bit what he is asking you. Ratio of their resistances, that is the first bit. So R1 is to R2 is to R3. I now can write L1 by A1 is to L2 by A2 is to L3 by A3. But what are these given values? You look at L1 by A1, it's 1 over 2. L2 by A2, 2 over 4. L3 by A3, that is 3 by 1, that is nothing other than 3. So what you can understand from this? This is 1 by 2 is to 1 by 2 is to 3. What is the other way of writing the same? 1 is to 6. So what is the ratio of their resistances is the first bit what he is asking, that you can write 1 is to 6. What is the second bit he is asking? Look at that second bit part of it. What he is asking you? Ratio of electric currents. I have already told you these three resistors are connected in parallel. When they are connected in parallel, you can all understand potential difference across each and every resistance remains constant. When potential difference across each resistance is constant, current is inversely proportional to R. That is the concept you need to understand. So, what is the ratio of currents? That is the second bit what he is asking for. But as I have already given you, current is inversely proportional to resistance. Then what can I write now? This can be rewritten as 1 by R1 is to 1 by R2 is to 1 by R3. That is the one. So R1 is to R2 is to R3 already we have taken up. So what will you get now? 1 is to 1 by 6. That is the concept. This 1 by 1 is to 1 by 1 is to 1 by 6. What is the corresponding ratio now? 6 is to 1 is to 1. That is the corresponding ratio. So what you should understand here, I1 is to I2 is to I3 is equal to 1 by R1 is to 1 by R2 is to 1 by R3. That now will be 6 is to 1 is to 1, like we people can take. Sorry, 6 is to 1, because we people are having 1 is to 1 by 6. 6 is to 1. That is the ratio, correct ratio. But remember the third bit, please. What is the ratio of their powers? Once again, let me explain you. What is the formula for electric power first? All of you can understand straight away. Power P is equal to either I square R or V square by R. Or you can even write VI. Voltage into current, or I square R, or V square by R. But observe carefully, out of the three formulae, which one should be entertained now? We cannot go by any equation whatever we like out of the three. What is the concept behind? In this circuit, you are finding that V is constant. When V is constant, you can go ahead with this formula. So, power P is equal to V square by R. Out of that, when V square is constant, what can I write? P is inversely proportional to R again. So, what is the method of writing the formula? It can be P1 is to P2 is to P3 is equal to 1 by R1 is to 1 by R2 is to 1 by R3. What is it again? 6 is to 6 is to 1. So, the way in which we people are finding the ratio of currents, same thing is repeated even in the case of powers also. So, what is the correct option? A tallies with R in the second table. B tallies with P in the second table. C tallies with P again in the second table. So, what is the correct option for us? A to R, B to P and C also to P. This is the correct match. And which match is correct out of the four options given? The answer for this one is the third match that is correct. If you look at the options given, A to P, B to Q, C to R, that is the first option, which is wrong. A to P, A to Q, B to R, C to P, that is the second option given, that is also wrong. Then what is the correct option? A to R, B to P and C also to P, that is the third option which is correct. And fourth option, of course, no need for us to look into, but okay, if you look at A to R, B to Q and C to P, that is also equally wrong. So, correct option for this particular match is that C, that is the correct one. But one thing you should all understand here, when resistors are connected in series, already I have made it very clear in the beginning today, currents will be the same. Current remains constant when resistances are connected in series. Voltage remains constant when resistances are connected in parallel. So, these two areas, if you are thorough with, easily you can understand the formula for ratio of powers. So, this is the question number 9 what we have in this order today. Let us discuss the 10th problem, the very next number in order. Let me read the problem first. A battery of internal resistance is connected to the network of resistance as shown in the figure. In order that the maximum power can be delivered to the network, the value of R should be how much? That is the question. What is the circuit given first of all, you see? Then you can identify what are the corresponding options given. First option given 4 by 9 ohm, second option given 2 ohm, third option given 8 by 3 ohm and fourth option is given 18 ohm. And correct option for this one is the second one. Second option is correct, that means 2 ohm. And remember, same question has been asked in JEE exam in 1995. So, such models we can expect anytime. Now, according to the given circuit, he said there are few resistances connected like this. Look at the way he has connected the resistances. He gave one here, he gave one here. And of course, one more resistance is connected across this. One more resistance is connected across these 2 points. and here this is connected to a cell like this, and that cell is now connected over here. This is the one. And what is this given? It is EMF is E, and he said its resistance is 4 ohm. What is this resistance to be called, please? It is called internal resistance of the cell. So whenever some ohmage is given adjacent to a cell, that resistance is to be called internal resistance of the cell. Now what are the values he has given? This is R given, this is R given. And of course this is R given, this also is R given. Now this is 6R, he said. This other ones, he has given you this one as R and this one as something like 4R. So this is the circuit. Now observe this circuit a little carefully. You can minimize the size of the circuit now, provided if you can understand which are in series and which are in parallel. So careful observation will make every one of you understand one point. Whatever current that enters into this resistance, same current enters into this resistance also. So what is the very meaning of that? Both the resistances are now connected in series. When current remains the same, it is understood resistances are connected in series. Same concept I can take again like this. Whatever current that enters this way, same current enters into this branch also. So what you should understand again? These two resistances are also in series with one another. The moment you can identify these two, you can totally minimize the size of the circuit. How to minimize that? Now you can understand. If I redraw the same circuit this way, first resistance R, next resistance 2R. This is R plus R. Next resistance here again 2R. This is R plus R. The next resistance over here as 4R. That is what has been taken here, 4R. Next thing, across these two, we people have connected a cell like this. That is the one. So you can take this one as EMF E and 4 ohm. Here a resistance of 6R that is given there. So you people can straight away understand that this value is given as 6R. This is R, R, 4R and R like this. So this is R, 2R, 2R, 4R, 6R, 4 ohm and E. This is the simplified form of this circuit. But immediately, the moment you have simplified the circuit, the very important most point should strike to your mind. What is that? We have a construction of such kind which is called Wheatstone bridge. Most of you must have got the correct idea behind that. When I consider 4 branches in which 4 resistances like P, Q, R and S are connected this way, a galvanometer is connected across these two, and a cell of EMF E is connected across the other 2 terminals. This is P. Now the moment you find P by Q is equal to R by S. P by Q is equal to R by S. Or you can even call it P by R is equal to Q by S. Observe the way I am writing the equation. P by Q is equal to R by S, or P by R is equal to Q by S, or Q by P is equal to S by R, or R by P is equal to S by Q. Whichever equation out of the four you want to take, you take. All are one and the same. There is no difference between any two equations, whatever I have just rendered. So here, if at all P by Q is equal to R by S, then current across the galvanometer will be 0. That is what is called the balancing condition of Wheatstone bridge. So one should immediately recollect from the concepts. What is the balancing condition of Wheatstone bridge? What is the balancing condition? If P by Q is equal to R by S, current across the galvanometer will be 0. Now what you should first of all try for is whether this circuit is Wheatstone bridge or not. Just compare. P by Q is equal to R by S. That is the condition I have written. R by 2R is equal to 2R by 4R. Exactly we are getting what is R by 2R? 1 by 2. What is 2R by 4R? Again 1 by 2. That means P by Q is equal to R by S concept is directly valid here. When it is valid, what is the result? Current through galvanometer will be 0. Current through galvanometer 0 in that case is similar to current through 6R resistance will be 0. So current across this one will be 0. When current across this resistance is 0, that resistance is of no use for us. Remember this point carefully. When a resistance in a circuit is not carrying current, that resistance is a waste resistance for us. Whenever a wire is there of resistance R, unless current passes through that, we should not consider that resistance anymore. So what we should understand now in this regard, the moment 6R is not carrying any current, then what is it understood? These two resistors are connected in series. These two resistors are connected in series and both are connected in parallel. So R and 2R, when they are connected in series, what is the resultant resistance? It is the sum of both of them, R plus 2R. 2R and 4R are connected in series, then what will be the resultant? It is 2R plus 4R, which is 6R. Now 3R and 6R both are in parallel. Then what will be the effective resistance? It is 3R into 6R by 3R plus 6R, that is 9R. Based on which formula we people are taking this? R1 R2 by R1 plus R2. That is the concept. Now 3R cancels thrice, this cancels twice. So what is the effective resistance, please? 2R. But his question is not that. What is the question he is asking? For the power delivered to be maximum. Power is maximum. Now immediately you should go back to a theory. What is that? Maximum power theorem. Most of you people might have read it like this only, the same name. Maximum power theorem. What is maximum power theorem? If power to be maximum, for power to be maximum in any circuit, what should be the condition, you know? External resistance must be equal to internal resistance. Observe this particular concept carefully. Maximum power theorem, what it says? For power to be maximum, net external resistance must be equal to net internal resistance of the cell. Now what is net external resistance? 2R. What is internal resistance of the cell given? 4 ohm. So what you can understand, if power to be maximum, if power to become maximum, if power to become maximum, what is the condition? Condition is simple. R effective must be equal to internal resistance of the cell. Internal resistance of the cell. So what is R effective here? It is 2R. What is internal resistance of the cell? 4 ohm. So you write this one as 4. Then what is the condition? R must be 2 ohm. When 2R is equal to 4, what should be R? It should be 2 ohm. Now see the options. Already I have given. 4 by 9 the first option, 2 ohm the second option, 8 by 3 the third option, 18 ohm is the fourth option. So what is the correct option there? It is the second option which is correct. So R should be 2 ohm. Therefore, answer will now be the second one B. But I remind you once again, what are the concepts we have taken to solve this problem? One is the case of Wheatstone bridge. When we consider a Wheatstone bridge, when the bridge is balanced, it's understood the current across the galvanometer will be 0. Then automatically, what is the balancing condition for the Wheatstone bridge? P by Q is equal to R by S. So that is one part of it which I have used here. And what is the second one? Maximum power theorem we have in current electricity topic. What is this maximum power theorem giving us? For the power to become maximum in any circuit, the net external resistance of the circuit must be equal to the net internal resistance of the cell. So external resistance and internal resistance, when they are numerically equal, the power across the circuit becomes maximum. So according to maximum power theorem, I have equated the net external resistance to the internal resistance of the cell. So it is 2R is equal to 4, then automatically R becomes 2 ohm. So out of all the 4 options given, second option is given as 2 ohm. So that is the correct option for us. So this is the answer for problem number 10.